Hello all, my name is Shubham and welcome to my YouTube channel. Today we'll be discussing a very interesting problem. So let's begin. Today's problem, majorly known as currency arbitrage. The problem is there is a discrepancies in the exchange rates among the currencies. So we want to transform one unit of a currency into more than one unit of the same currency. For example, you have one US dollar, and that helps you to buy 0.82 euro. 1 euro bought 129.7 Japanese yen. One Japanese yen bought 12 Turkish lira, and one Turkish lira bought 0.0008 USD. So when you see that if you buy one USD, you'll get 0.82 euros. With these euros, you can buy one these many Japanese yens. With this, you'll be able to buy 12 liras, and with these many liras, you can buy again this many USDs. Now, with these exchange rates, if you see, the total comes approximately the product of all the exchange rates. If you do, it comes to 1.02. So, if you see, with one USD, you were able to buy so many currency exchanges, and with that help, you were able to convert that one USD to 1.02 USD, making a total profit of 2%. So, with these discrepancies in the exchange rate, we want to see if a trader can make a profit. To formalize this definition or this question, suppose we have been given n currencies, which are known as C1, C2 up to Cn, and we have an n cross n table with R of exchange rates, such that one unit of currency Ci buys R I comma j units of currency Cj. For example, this is what we have to do. We have to find uh, we have been given different currencies C1, C2, C3, and their respective exchange rates among themselves, and we have to find an efficient algorithm to see if currency arbitrage exists and can a trader make a profit. Mathematically speaking, if you have C1, C2, C3 till Cn currencies, right, and their exchange rates are, let's say, R1, R2, R2, R3, R3, R4, dot, 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 RK1. If we are able to find a cycle or a combination of currencies such that their product is greater than 1, just like in this case, if you see, when I multiply all these exchange rates, I'm able to get a product total as 1.02, which is greater than 1. So if I'm able to find a cycle, right, with different exchange rates product, when I take the product of their exchange rates, and if that total product is greater than 1, then I can say for sure that I'll be able to make profit. So ultimately, what we have to find is R1, R2 dot 3. Now, clearly, this is a difficult problem to identify. Like, how can you find a cycle such that the product is greater than 1? But if we apply a logarithm on both the sides of this equation, then can we make something out of it? Let's see. So the formula of logarithm x, y, z dot dot dot, it actually is equal to sum of logs of each of the component. Using the same, now we can make it like this: log of R1, R2, log of R23 plus log of R34 dot 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 log of RK1. That should be greater than log of 1, which is 0. Now, if I kind of rewrite this equation further, then it can be written like this: log of summation of log of R I comma I plus 1, uh, where I ranges from 1 to k. And when k becomes when I becomes equal to k, we can just make I plus 1 equals to 1. So if we do this minus, then this equation becomes like this. Now, if you see, this is nothing but asking us to find if there is a cycle, if a cycle exists such that the sum of the logarithm of the weights is less than 0. Sorry, the negation of the sum of the logarithm of the weights is less than equal to 0, is less than 0. Now, ultimately, we have to find a negative cycle, and this can be achieved by one famous algorithm known as Bellman Ford. Now, in Bellman Ford, the idea is you have been given a graph G which has V vertices and E edges, which consist of weights. If you run the algorithm V minus 1 times, and if you are able to find or relax this condition that the distance of V, if it is greater than distance of U plus the weight of the edge, UV, if you are able to find these conditions, then we can continue to relax the edges. And we do this relaxation process V minus 1 times. And finally, we do the same process again one more time and see if the relaxation is still happening. If that happens, then we detect that there is a negative weight cycle. And that's all we have to do as part of this problem as well. So in Bellman Ford, we have V that is equals to total C currencies. We know the edges, and for each edge, we have to take minus negative log of the weight. This transformation is what we will require when we'll be creating the adjacency list. And then we run V minus times the algorithm for each node or each vertex. We'll try to relax the edges weight. And finally, we will do the same process one more time and see if we are able to relax. If yes, then we can say with confidence that there is a negative cycle, and we will return true from Bellman Ford. And that true indicates that the trader will be able to make a profit. So let's quickly see the implementation here. In Bellman Ford, I'm starting, I have a start currency and an exchange rates map. For this, we will require an iterator to iterate the map. We will require an iterator of the map. We will also require a distance array to store the distances. In the beginning, we will have to initialize the distance array with maximum value. Right? So we can have iterator equals to exchange rates dot begin. Here, I'm setting the distance of every currency from the source currency as maxima, which is int max in C++. Now, obviously, the distance of the start currency would be 0. So I'm setting it again here. Now we are going to, as I said, we are going to run v minus 1 iterations, and within each iteration, for each edge, we would be trying to see the relaxation. Now, I'm not sure if you are aware, but Bellman Ford is an algorithm which tries to find the shortest distance from the starting node. So that's what we're gonna do here. Let's say you have v as exchange rates dot size. V represents the total number of currencies. I'm going to run the outer loop v minus 1 time. Now for each edge, we have to drive the same thing. Now we have to cover the every edge of this particular uh, currency. So I'm going to traverse the adjacency list of it. Mm, let's say you have here exchange rates you have, and for each of the rates, we have to find two things. That is string v current, sorry, uh, will be rates of j dot first and double rate. That is going to be rates of j dot second. So you have now your source, you have your destination node, and then you have a rate. All you have to do is check if distances of v current is greater than distances of u current plus the rate. If that is true, then you relax the edge with this. Now, as I said, you will continue doing this v minus 1 time, and finally, you'll do the same thing one more time. Now, at any point of time, if this condition holds true, it means we have detected a negative cycle. So we are going to return true. And here we'll change it as bool. So this is the code of it. Now let's quickly see the time and space complexity. If you see, we are running the outer loop v minus 1 time, and then finally we are running it one more time. Now within this v minus 1 time, we are traversing every edge, right? And for each edge, we are relaxing. We are checking if it relaxes the weight or not. So to do so, we are traversing the adjacency list. So it will have v nodes again. And for each node, the number of edges is what we are going to travel. So the complexity is v minus 1 into v plus e times. And then we run the same algorithm again for v plus e. So total complexity is v plus e. That's all from my end, guys. Thank you.